Okay, this next one has to do with integrating polar coordinate systems, and this is actually should make complete sense to you. It starts with the fact that the area of a circle, which I'm going to draw as a little circle with a center, is equal to, you guys know it's equal to pi r squared, but what may not be evident is that pi is 1/2 tau. If you remember, tau is the entire circle, pi is half of that. This is actually somewhat critical because if the area of the circle is 1/2 tau r squared and tau is the whole, then the area of a sector of a circle is 1/2 theta r squared. Whatever radian angle that is, tau is the whole circle, so partial circles can be replaced with bits. And this becomes the entire thing we use to do the integral of involving polar curves. So let me kind of explain to you what we mean by that. I'm going to draw an example of a polar curve, and we're going to do one of the sphenoids or cardioids, which I'm going to just kind of do like this. Actually, I should make it less heart-like and make it more kind of like, okay. And we want to do the area between polar curves. So first we're going to do the area under the polar curve, which is going to look like a little pi wedge, a little sector. The first thing I want to do is I want to deal with what the limits of integration are. So these are going to be defined in terms of two angles, alpha and beta. So the limits of integration are theta values. In this case, alpha and beta, two angles in radians. And then finally, we're going to take this area of the sector from above, the 1/2 theta r squared, and we're going to integrate this. I'm going to pull the 1/2 out as a constant multiplier, integral from alpha to beta. My radius r squared is actually a function r of theta squared, and then d theta. My angle actually becomes the accumulation of an infinitely small number of those, and this is the formula for what in essence is the area. So I want you to find, as an example, let's find the area of one petal of r equals 3 cosine 3 theta. So r equals 3 cosine 3 theta, we can sneak over and let's look at a graph of what this looks like. So knowing that you can graph these by hand, I kind of want to separate skills out and just have it so that you can look at a single bit of it. R equals 3 cosine of theta cosine 3 theta, my bad, is this. So one petal, we want to kind of sneak, what does one petal of that look like? We're going to come back here and let's get 3 cosine 3 theta. I know that I've got a piece here, and if I plug in theta of 0, I get 3. So 0, 3 is an ordered pair. And I know that I want to figure out where this comes back in. So what I want to do is I want to, this is theta and this is r, I want to solve for 0 is equal to 3 cosine of 3 theta, and just find me two theta values where that happens. Where is the cosine of 3 theta equal to 0? That happens anywhere that 3 theta is equal to pi over 2. And another one, that would be this one, another one would be negative pi over 2 if I want to actually go the reverse. Those are two places where the radius is equal to 0. So if I divide by 3, this means theta could be pi over 6 or theta could be negative pi over 6. And that actually should kind of make sense based on what you're seeing. We know that this is swinging back in like this and also doing the same thing here. So theta is pi over 6 is this angle, and theta is negative pi over 6 is this angle. So if I do an integral from negative pi over 6 to pi over 6, it's sweeping this area all the way up there. But we need to actually do the integral properly. So the integral of Well, I can do the integral from negative pi over 6 to pi over 6, or I could do 2 times the integral from 0 to pi over 6, because that is going to be twice this area here, which now even makes better sense to do. Also because then we get to multiply by the 1/2 r of theta squared d theta. So 2 times the 1/2 is 1. We get the integral from 0 to pi over 6. My r of theta is 3 cosine of 3 theta squared d theta. And then I get 3 squared is 9. So 9 times all this gives me, let's see, bring that out. I get 9 times the integral from 0 to pi over 6 of cosine squared 3 theta d theta. Okay, now how do I deal with the cosine squared? You need to know the integral of cosine squared, and you need to know it in the sense of a substitution. We know that the cosine of 2 theta is equal to 2 times the cosine of squared theta minus 1. This is one of those must-know cold facts. So if I solve this, I get the cosine squared of theta is equal to the cosine of 2 theta plus 1 over 2. So then the cosine squared of 3 theta should be equal to the cosine of 6 theta plus 1 over 2. That's the substitution we're going to make right here. I'm going to pull out the 1/2 and get 9/2 times the integral from 0 to pi over 6 of the cosine of 6 theta plus 1 d theta. As an integral now, I get cosine of 6 theta over 6 because of reverse chain rule, plus a theta evaluated from 0 to pi over 6. Now we plug everything in. I get the cosine of pi over 6 plus pi over 6 minus the cosine of 0 over 6 plus 0. This ends up being, that goes away, and I get 9/2 pi over 6 minus cosine of 0 is, oh, you know what? I did my integral wrong, and you guys probably all caught that because you're awesome. The integral of cosine is sine. Here, I'm not even looking at my own notes thing. So I get the sine of pi x, or pi, that's why that's a 0. Then I get the sine of 0. So not only does that go away, but that goes away, and I just get this, which when you simplify is 3 pi over 4. Done. Okay, next we're going to do an example of one where I want you to find the area between the inner and the outer loop of the limaçon. I know. I had to actually look that word up on Google to see what it said. Of the limaçon, it's an O-N, but it's a funky C, r equals 1 minus 2 sine thetas. And limaçons happen whenever this relationship is, whenever you're subtracting 1 minus 2 and you're getting a negative number. So as a graph, which I'll kind of graph this for you again, sine of 0 is 0. So when theta is 0, you get 1 minus 2. You get a negative 1. And then it moves out to the maximum of 3. Then it moves back to 1. Then it goes to 0, and it loops in. So when theta is 0, it's 1. When theta is pi over 2, you get negative 1. So it moves up like this, and it goes to negative 1. Then it moves out. Then it moves down. Then it moves back up. That's the limaçon. And I want the area between the inner and the outer loop. So I want this area here. Well, we need to figure out when does theta cross the, or sorry, at what theta, I should say, at what theta is r equal to 0? Well, that's basically asking when is 2 sine of theta equal to 1, or when is sine of theta equal to 1/2. And that's going to happen when theta is equal to pi over 6 or theta is equal to 5 pi over 6. So when I moves here, the inner loop area is basically the area from, well, we have to do the 1/2 pi r squared or theta r squared thing. So the inner loop moves from, let's kind of look at how this is tracing. This is pi over 6, and then it traces an area here, and this is 5 pi over 6. So the first time that this passes, remember we started here, we moved, and then it passes theta's pi over 6, then theta's 5 pi over 6. And you can actually kind of see that. If you look at tangents and see how this works, this is a theta of pi over 6, and then this is a theta of 5 pi over 6. So backing up, the inner loop is the integral from pi over 6 to 5 pi over 6, 1/2 times 1 minus 2 sine of theta squared d theta. So then we go for the outer loop, and you got to get really clever with the outer loop. The outer loop starts as the integral of 5 pi over 6. So we're starting with this point here, then we're tracing this completely back around again as it passes through 2 pi. 2 pi being theta is 0 again, and it moves to the next iteration. So we're starting with 5 pi over 6, but we don't want to go back to pi over 6 because we're going to get a negative. We want to do pi over 6 plus 2 pi. We want to move a complete cycle. And this is the same integral, 1 minus 2 sine of theta squared d theta. So the area total is equal to, I'm going to factor the 1/2 out, the integral of 5 pi over 6 of 13 pi over 13 pi over 6, because that's the sum pi over 6 and 2 pi, of 1 minus 2 sine of theta quantity squared d theta minus, we're going to keep that factored out, the integral from pi over 6 to 5 pi over 6 of the same thing, 1 minus 2 sine of theta squared d theta. Okay, moving into how to integrate this, we're going to do 1/2 13 pi over 6. I'm going to have to expand. We're going to expand this 1 minus 4 sine of theta plus 4 sine squared theta. Keep that factored out. D theta minus, I'm going to put a little dot, dot, dot there because I know that's poor math, but we're just going to do this part here and then we'll bring it all together. The 1 minus 4 sine theta, I want to do a substitution because you also know that the cosine of 2 theta is equal to 1 minus 2 sine of squared theta, which means that 2 sine squared theta is equal to 1 minus cosine of 2 theta, or 4 sine theta, which is what this is equal to 2 minus 2 cosine 2 theta. So this is plus 2 minus 2, that should be a cosine, 2 cosine of 2 theta d theta. And I'll bring all this back together here in a minute. I just want to get moving on this. 3 minus 4 sine of theta minus 2 cosine of 2 theta. Still have an integral. So now we get 3 theta as an integral minus the integral of sine is negative cosine. So this becomes plus 4 cosine of theta minus sine of 2 theta. And this is going to be evaluated from 5 pi over 6 to 13 pi over 6. Then I'm going to subtract the same thing. So 4 cosine of theta minus sine of 2 theta. And we're going to evaluate that from pi over 6 to 5 pi over 6. And all of this is going to be multiplied by 1/2. So let's do this. 1/2. 3 times theta is 3 times, so this is 13 pi over 2 plus the cosine of this is the same as the cosine of pi over 6. So that is root 3 over 2. So 4 times that is 2 root 3 minus the sine of twice that. So the sine of, let's see, the sine of 13 pi over 2. 13 pi over 3. And 13 pi over 3 is, that is coterminal with, let's just keep subtracting 6's. That's coterminal with pi over 3. And the sine of that is root 3 over 2. Minus, then I have to do 3, so this would be 5 pi over 2 plus 4 times the cosine of 5 pi over 2. Cosine of 5 pi over 2 is a negative root 3 over 2. And then minus the sine of twice that. So the sine of twice that is the sine of 5 pi over 3. 5 pi over 3 has a sine of negative root 3 over 2. Okay, so then that's all in parentheses, minus. I already did this set here, so I just copy the set over. 5 pi over 2 minus 2 root 3 plus root 3 over 2. And then minus, I should put that in parentheses, minus 3 times 0. 4 cosine of 0 is 4. And then the sine, oh, sorry, and this is not 3 times 0, it's 3 times that. So pi over 2, then plus 4 times the cosine of pi over 6 is that 2 root 3 minus the sine of this is root 3 over 2. Whew. Okay, then you combine like terms. So let's start underlining let's highlight this, 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 and this. And let's keep our signs straight. So 13 minus 5 is 8. Then 8, this would be minus 5 is 3. This would be minus a negative, so plus 1, 4. So 4 pi over 2, 2 pi. Now let's look at these. And this right here is really just negative 2 root 3. So 2 root 3 plus, that'd be 4 root 3 minus a negative is 6 root 3. And then this would also be minus a negative. And that's 8 root 3. So plus 8 root 3. And finally, let's change highlight colors. This right here, this, and this. Keep these straight. So minus, this ends up being positive right here. So this minus itself is 2 in the numerator, 3 in the numerator, and then this becomes a plus. So 2 in the numerator, 2 root 3 over 2, so this is plus root 3. And this ends up being pi plus 9 root 3 over 2. Hope I did that right. That's it.